First of all, huge thanks to Kaspersky for having me here. It's a huge, huge honor. I'm extremely happy to be here. So today you've seen a lot of talks on the defense. So what we as a defender should do to secure industrial control systems. So this talk will be more concentrated on the offensive security because this is where my area of specialization. I do a lot of, mostly specializing on offensive security because if you know how the attack works, then you can figure out how to stop the attackers. So basically know your enemy, this mouth. So typically, attacks are described with attack life cycles. It's a common method to describe a process of conducting a cyber attacks, and there are multiple models exist. So one of those is a MITRE ATT&CK, which is adversarial tactics, techniques, and common knowledge framework. And together it reads like MITRE ATT&CK framework. So ATT&CK stands like we read it as attack. And it's a globally accessible knowledge base of adversarial tactics and techniques based, and this is a keyword, real-world observations. So this is how it looks for the enterprise networks. There is a similar framework exists for mobile networks. And recently, they started developing a similar framework for industrial control systems. So this is a pilot. This is how the pilot version looks like. That's not the public version, which is later, once they will finalize it, they will release it publicly for public comments. But that's how it's looks, intermediary version. And they describe the adversarial techniques from level 0, which is physical process, to level 3. So basically for physical process and control infrastructure. So they're not talking about servers in the level 3, like historians and so on. So important disclaimer, this work is based on my own thoughts and considerations, so no warranties that whatever I will say today as an expert will later find the way or its place in the MITRE framework, but it may. So what is the motivation of giving this talk? I'll take you back to the history a little bit. So that's 2015 and my Black Hat talk 2015. So this was the first time when I took an entire chemical plant and I wanted to design a full attack on it. I wanted to cause persistent economic damage. And I did not know where to begin with. So I look at the plant, how do I make it being less profitable? So there was no any framework or guidance, how do I approach of executing this task? It's a gigantic task. So I found this presentation from Jason Larson, which is, he gave a talk in 2006, and there were stages of SCADA attacks. There was no description for these stages, there was no guidance how to use them, but these 5 words, that was all what I had. So that's better than nothing. So I took the stages and I tried to apply it to, basically, I went through all of the stages, hoping that that will lead me to full damage payload. And it worked out. It was difficult. I had to figure out which tasks needs to be accomplished at each stage, but I was able to do so. So eventually I was able to write my working exploit. There is another, so basically, I've been working with this framework, basically with this cyber physical attack lifecycle for many years. I applied to different processes, continuous and discrete processes, and there is a lot of several public works of me using this attack lifecycle to design attacks, cyber physical attacks. There are several works which I did non-publicly. They were proprietary, but this is an excellent model which works. There is another model, so this is called timing and state diagram, which is also was presented actually by Jason Larson at RSA. To my memory, they call it a Curtis diagram by the name of the guy who created it. This diagram mostly concerns about already executing attack in a target industrial environment. And you could see that there are slightly different words for different stages, or let's say tactics, like start condition learning, control spoof, and so on. But in reality, if we will map them to the stages of cyber-physical attack lifecycle, it's totally mappable, and it's exactly that sequence and exactly those activities. So as an attacker, when I look at something like MITRE ATT&CK framework, I would like to see my tactics and my techniques in that framework. So I would be searching for my activities, for my methods in that framework, because at the end, you're trying to describe the attacker. So it seems like these two frameworks would have a good beginning. And I moved a little bit further in my discussion. I have another slide here. So this timing and state diagram, it's really more concentrated. So mostly when people think about cyber-physical attacks, they think mostly about cyber component of it. Like, how do we write the code? How do we manipulate network traffic? How do we spoof sensor, like basically rewrite sensor value in a packet? But those are all cyber techniques. So this presentation was solely concentrated on the control and engineering part of the attack. And I actually wanted to show a video of how it looked like, because it was an implosion, and it's really fantastic work. So yeah, there was a slight delay in the big boom. So it seems like, as I just previously said, it seems like we have already a couple of frameworks. So we have some material to start designing this ICS MITRE ATT&CK. But the problem is that me and Jason Larson, we are not the real-world APTs. We are researchers. And the MITRE is trying to build their framework based on the real case scenarios. So now we have this chicken and egg problem. We want to create ICS attack, but we do not have attacker in the wild or enough. We just have 3 cases so that we could reliably populate all of those tactics with techniques. So which one should come first? Because it seems like we only have researchers right now. We don't have attacker in the wild. So I came up with this fantastic idea. Yes, so if we will wait, what I wanted to say, so if we will wait too long for attacker in the wild, you know, we may never have this ICS attack framework. So that's why, in this case, patient is not a virtue, and I came up with this fantastic idea. How about call us, researchers, an APT, if management insists? So, and then you can have all of this traditional threat intelligence and attribution game, like, for example, new researchers and research groups are monitored first as unclassified threat actors. And then after producing a significant amount of coherent offensive research, you can graduate them into the APT. So for example, like Jason Larson APT, yeah, the most advanced out there, or APT Alexander Bolshev, always does the weird things, or APT Marina Krotofil. She seems to work between many other APTs, so confusing. Like she worked with APT Jason Larson and with APT Alexander Bolshev. Does it mean that Larson and Bolshev are working together? Because that would be worrisome, because if you combine advanced and weird, there's a strong power. So of course, it's all a joke, but I do believe that researchers' work needs to be taken into account, and I think actually the real APTs and researchers, we are all learning right now how to execute cyber-physical attacks in the ICS domain. So let's start with the main part of the presentation. So what are my considerations? What should be there in that MITRE attack framework? And we start from the end, like process control and physical damage, because that's the most critical part of the cyber-physical exploitation. So I'll give you some examples on a specific example of the physical damage scenario. So it's been my very long-term dream to kill a water filter from the water treatment facility. So I never had access to a water treatment facility, but finally I was able to conduct experiment in a real, like full-size test bed in the Singaporean University of Technology and Design, and I'm incredibly grateful for Professor Aditya and his student for conducting this experiment for me on demand. So if we kill the water filter in the water treatment facility, we interrupt the supply of water, very bad. So if I would look into this, this is the last tactic in this attack framework, physical impact, there will be certain techniques available, like which described attacker techniques to cause physical impact. And examples include modify reporting setting, modify tag, module firmware, masquerading. But honestly, I don't know how any of these techniques will result in damage, physical damage of the filter. So I can't use any of these techniques to destroy the filter. And the problem with this is that filter is a physical or engineered object, and we would need to use tactics from the physical world in order to cause destruction to the filter. So, and that's the point is that cyber-physical system, or let's say industrial control system, always consists logically out of 3 layers. It's physical layer, control layer, and cyber layer. And as an attacker, I would need to exploit at all of these 3 layers. And my techniques will be different and unique to every layer. So in the physical layer, it will be techniques which are completely different from control and cyber. And cyber, at the end, it's just implementation of my techniques in control and physical layer. And when we start designing a damage scenario, it's always start at the physical layer. So let's start planning our attack. For that, the best way to begin with is to read documentation. So every documentation, so I've just pulled like a couple of manuals of 2 famous brands of these ultrafiltration filters. And there are different dangerous, like harmful things to these filters. For example, impurities in the water, like inclusions like particles or oil things, they will destroy the membrane. But that's a very bad damage scenario because it will be difficult to pull it off remotely, and it's not very reliable scenario. But what is more reliable is that the membranes in the filter are very susceptible to the overpressure and overload. So I basically need to overpressure the membranes so in order to destroy them. So overpressure seems to be doable. So for that, of course, I will need to further understand the process. We will talk about that. And this is the point number 1, which I wanted to say, that when we talk about, for example, tactic like physical impact, I think that the tactics which should be there should be these types of the physical attacks on the engineered systems. And the example includes, for example, this is what you see, classes of physical damage, inertial attack, exclusion, resonance, wear attacks, surge attacks, latent abilities. This is from J.C. Larson presentation, again, 2006. So, for example, in this specific case, when we talk about overpressure, that will be a surge attack. So I will apply a surge attack technique to destroy the filter. So now how we will do it, that's already, I will need to start doing my typical attacky things. So basically, I will start to look at their HMI and piping and instrumentation diagrams. And if I read their documentation, I will know that backwash and water filtration should never happen at the same time, because one is filtering the water, another is cleaning the filter. But what if I can make them flow in together at the same time to the filter? It will be a high load, basically, and overpressure. So then I will probably start grabbing other documentation on this backwash stage and so on. And one would think, if I go slightly back, maybe here, one would think that, well, now it's all easy, we understand. So let's just execute a cyber attack by starting the pumps and open the valves, and basically we are done, and the water will flow. The problem is we always have still a control layer. The control layer knows that these 2 flows should never happen at the same time, so they will not allow you to do so. So the attacker would need actually to figure out how to prevent this interlock in the control system. So for that, so for example, there are 3 events which trigger backwash, like preset time every 30 minutes, UF filtered, like when the pressure is too high, like more than 40 kilopascal, or plant shutdown. So the attacker would need to take into, need to know how to trigger these events. So we will need to go to one, and all of this control logic is this, you cannot see it on the HMI. You really need to go and grab the control logic. So, and because the two stages are involved, you will need to go to pull the control logic from two PLCs, find all the necessary flags, defeat all the necessary conditions, which is not, like, it's a complex attack, which is not part of this, like, discussion. But the point is that eventually we will be able to execute successfully in cyber attack, and all of these two flows are now flowing through the filter. So now let's see what a maximum pressure we can achieve. So the average pressure in the filter is 12 to 13 kilopascal, and the maximum differential pressure which we were able to achieve was 98 kilopascals, which is around 1 bar. But the damaging pressure is 2 bar. So now we see that the attacker is actually not almighty. We have a fantastic, workable physical damage scenario. We successfully executed the cyber attack, yet we are not successful because we are still not damaging the membranes. So now, for example, in order to fix this attack, I would need to think about some techniques in the control layer to make sure that we maybe cycle valve in some strange way so that we will create more pressure, or maybe I can do some magic with controlling the pump that they will be pumping slightly faster, but now I will need to use some magic from the control layer. So techniques from the control layer. I don't know what exactly I would be using in this case because I don't know this infrastructure well enough. But in general, we already know several techniques from the control tactic. So, for example, one of them is stale data attack, which was discovered by me in 2013, where we try to lock in the memory and old data. So we basically make the process, the control logic, operate on old data, which is a stale data, which is not relevant to the real state of the process anymore. And if we will combine together the knowledge about the time constants of the control loop configuration and state of the process, and we will strategically lock in the memory a specific stale data, then we will be able to manipulate the process at will, bring it to the state which we want. And the beauty of this attack, because we are not manipulating the packet, but rather delaying or dropping the data packets, this attack can be executed on authenticated and encrypted traffic. So Jason Larson actually did a couple of follow-up attacks where he actually was executing these attacks on the encrypted traffic. So another technique which actually comes from Jason Larson is multi-adaptive control. We presented it together at DEF CON 2015. In this case, the attacker is writing an algorithm which actually destabilizes control loops. So normally the control loop should be minimizing the error, and the attacker tries to maximize the error. It means that the system will never be able to reach a set point. So for example, if you think that the robotic hand has to reach a certain position and, like, for example, grab something, you will try to destabilize it and make sure that the control algorithm will never be able to reach the right point because you're maximizing the error. So the third type technique is a skip frequency attack, which was discovered and presented by Reid Whiteman. In this case, so all rotating equipment has a native frequencies at which it starts vibrate. These frequencies are unique to each piece of equipment. You will find them in manual, and then in the control logic, those frequencies will be specified. And even if you try to change the frequency, you will always skip this one because it will cause vibration. But at this frequency, the equipment can be destroyed very quickly. So there are probably more. This is the third one which came to my mind first, but there are already known techniques from this control tactic. Next, let's look at the attack execution and detection avoidance, because this is also a big part of the MITRE framework. So for example, one of the tactics which is currently in the model is operator evasion. The problem is, yes, we need to evade operator intervention, but operator is not the only component from the, which we, let's say, from the control infrastructure which we need to evade. So the point is that control loop, in general, is having this hierarchical structure. So to begin with, the number one, what the attacker needs to evade or prevent response is from the control system itself, because the control system will always try to keep the process at the set points. The attacker will try to move the process away from the set points because he wants to cause physical, like damaging effects. So the control system will fight back. The operator will fight back. So the attacker will need to make sure that the control system and HMI system do not respond to his activities. And there is also even higher level of control loop infrastructure. This is process optimization application, because right now we have a lot of this predictive maintenance. We've seen the talk previously. For example, especially for rotating equipment, there will be another work stream where specific, for example, rotating equipment is instrumented with sensors, and the data is sent to the cloud, and we perform a lot of artificial intelligence and machine learning, and we can detect the real state of the equipment. So the attacker may blind the control system and the operator about the true state, for example, of the rotating equipment. But then we still need to blind also the advanced application, optimization applications. So in general, we have like operator evasion, control system evasion, and advanced control evasion. So maybe we can actually combine them together and call this tactic as response prevention. Just an idea. And also in the techniques from this tactic, while I see here modified tag or rootkit, I'm kind of more inclined to give this tactics more vocabulary, a flavor of process control and process engineering, like to be a little bit more specific and having specific vocabulary, like, for example, alarm avoidance. That is a powerful technique to evade operator intervention. Or, for example, to blind all three layers of control. Process variable modification, basically forging sensor signal, is a powerful technique. Actually, there is a large body of literature and work done on the stealthy attacks, when the attacker is making such a small changes to the process that control system and control algorithm remain blinded to these small changes while the process is already degrading. So there is a lot of approaches. It's called stealthy attacks. So that would be another technique which would belong to this tactic. Another one which I was excited about, this one, command and control. While this is so relevant to process control, obviously there is command and control. But typically when we think about command and control, we think about, for example, human or implant, or basically malware talking to the C2 server, downloading additional tools, or basically human operator who is talking to the implant in the network. So this is typically how we think about command and control. But the point is that, of course, we have a command and control in industrial control systems. So we have similar scheme. So for example, if we have a human in the control network, he will be talking to the field instrumentation and to the physical process and receiving feedback, like observing the process state. Or if we talk about implants in different parts of the control system, or like say factory or plant, they will be also talking to each other in order to trigger different payloads at a different time, at needed time. So basically, yes, we do have, but techniques for this command and control, when a human or implant talks to the physical process, they will be different from techniques when a human or implant talks to the C2 server in the internet. So maybe that's why it makes sense to rename it. So, because otherwise people will be confused and will be thinking about normal C2 communication in the internet. So maybe we could rename it as execution and feedback, because there is this next to the, so command and control, it's actually the execution tactics in the MITRE framework, and then we always need a feedback, because we always need to know if our attack is successful. We need to always observe state of the process to know that the process is doing what we want it to do. So number 4 point, so which tactics do we know from the feedback? which techniques do we know from the feedback tactic? And for example, that implosion experiment which I showed you at the beginning, let's imagine that we want to make implosion on the pipe, for example, water or gas pipe. So, for example, how do we know that our attack was successful? We are sitting remotely somewhere far away, we can't see, and there is no roundness sensor which will tell us whether it's already imploded or not. So, for example, one of the indirect ways to do so, like, is to observe the pressure in the pipe, and typically this sensor will be available. So, for example, if there is a protection which is like vacuum breaker, then we will not be able to execute our attack. So once we see, for example, this artifact which you see circled in red, then we know that our attack is not successful because there is a vacuum breaker, and yeah, we will not be able to finish the attack. So one of the feedback techniques is just basically observing state of the process in sensors. Another technique from Jason Larson is sensor proxies. He presented it as for 2015, where he converted some physical button into the microphone in order to measure, like, basically sound, like, for example, noises done by the rotating equipment. I use technique proxy measurements. This is what I used in Black Hat 2015. For example, reactor exit temperature in a chemical facility is a proxy measurement, which basically like almost estimation for production rate of a useful product. So basically, by just observing the reactor exit temperature, I can use it as a proxy measurement for concentration of the useful product. Another technique which I used was detection of process state. So here, for example, this is what typically I use for feedback mechanism between different implants in the physical process. In the plant, for example, I have implants in different parts of the plant, in different PLCs. So I would say that, hey, as soon as you observe this state, you need to trigger payload XYZ. Another technique, reading state machine, it's straightforward. Building process models, that is Jason Larson was doing, estimations, like when you try roughly estimate what's happening. It's a technique, and calculations, which I previously also used. So, conclusions. I'm actually doing well in time. So what are the other points to consider? So obviously, you know, like I had only 30 minutes, and of course I have a lot of thoughts, so I had to limit myself to only some points. So the last point, which I wanted to discuss. So physical damage techniques, obviously not limited to breakage, which I showed you on the slides, but there are also techniques for degradation. So one of the major points for MITRE framework is that they always consider those techniques which are detectable because they want to compare how well we are doing with defenses. And for example, all of those techniques which I've been showing you, like damages of physical, classes of physical damage, they are all detectable by engineering methods. But in general, for example, because like stale data attacks is detectable, for example, at all levels, cyber, control, and engineering methods. So the point what I'm trying to make is that all of those techniques which I've been showing to you, even though they're unusual for people from cyber domain, they're all detectable. So they can be good candidates for this attack framework. I think that we need to increase especially coverage in this framework for techniques, especially for cyber techniques for embedded and IoT systems, because the PCs and mobile exploitation is already covered by the enterprise and mobile MITRE framework. So we need now to cover more embedded, because the techniques will be completely different. For example, persistence will be different in embedded than in PCs and IoTs. And the very last point, which I named 42 because it's a perfect number. So I don't know, I discovered just recently that there is actually a pre-attack MITRE framework. I never knew that it was before, and it was something what I was actually missing in the enterprise attack framework. And it covers tactics and techniques from the pre-exploitation. So basically, the attacker does a lot of work in advance before starting exploiting the target. They go to the third parties, they collect this OSINT, conduct a lot of OSINT investigations, and so on. So this is actually even more important stage in the ICS. So for me, that would be my access stage from my attack life cycle. And I actually extensively covered that in one of my recent talks at Troopers. So because there will be a very long phase, and the attacker will do a lot of pre-exploitation, like basically go into third parties, for example, looking for the damage reports, maybe go into the vendors, implanting the devices and software and so on. It's a gigantic stage which will define the targeting, the damage scenario, and so on. So this is something what is this pre-attack framework also needs to be developed for industrial control systems. That was it from me. Thank you very much.